Welcome back to Summarize Science. Today, we're looking at a fascinating question. Can an AI learn the laws of chemistry all on its own, without being given any hints? Understanding how molecules bend, twist, and interact is fundamental to everything from creating new medicines to developing better batteries. For years, scientists have used specialized AI models called graph neural networks, or GNNs, for this. Think of GNNs as being given a cheat sheet. They're explicitly told which atoms are neighbors and should talk to each other, based on how close they are. But this approach has limitations. It's like forcing the AI to only look at its immediate surroundings, which can be slow and rigid. This new paper asks, what if we throw away the cheat sheet? What if we use a transformer, the same kind of powerful, general-purpose AI that powers models like ChatGPT, and just feed it the raw positions of atoms in a molecule? The researchers' goal was to see if this blank slate AI could discover the fundamental rules of molecular structure by itself, and the results are pretty stunning. First, they found that their transformer model performed just as well as a state-of-the-art, specialized GNN at predicting molecular energies and forces. In fact, as shown here in Table 1, the transformer was actually faster to train and run, thanks to better software and hardware optimization. But here's where it gets really interesting. The researchers tested how the model improved as they made it bigger. Just like we've seen in language AI, they discovered a predictable scaling law. This graph shows that as you add more parameters to the model, its performance gets better in a smooth, predictable curve. This is huge because it means researchers can reliably forecast how much better their models will get with more computing power, removing a lot of guesswork. So, the model is good, but what did it actually learn? When they looked inside the model's brain, they saw it had learned a core principle of physics entirely from the data. This chart shows that the model learned to pay the most attention to atoms that are physically close to each other, and less attention to those far away. No one programmed this rule in. It emerged naturally. Even more impressively, the model learned to be adaptive. This graph shows that for an atom that's isolated and far from others, the model expands its attention radius to look for interactions further away. But for an atom in a densely packed area, it focuses only on its immediate neighbors. It's like the AI developed its own flexible, common-sense approach to chemistry. So let's recap the key takeaways. A standard transformer AI, without any built-in chemistry knowledge, can compete with specialized models. These models improve predictably with size, providing a clear roadmap for future development. And most impressively, they can independently discover and apply flexible, physically intuitive rules about how molecules work. What does this mean for the future? It could point towards a more standardized and scalable way to model the molecular world. Instead of building custom AI for every problem, we could have large, powerful foundation models for chemistry, much like we have for language. This could dramatically accelerate the discovery of new drugs, materials, and chemical processes. It's a powerful demonstration that sometimes, giving a powerful learning algorithm less guidance can lead to more impressive and flexible results. Thanks for watching this episode of Summarize Science.